Hi everyone, thanks for joining today. My name is Rich Markley. I'm a product manager for Rohde and Schwarz. Today, as part of our Test Essentials series, we're going to focus on spectrum analysis basics.
So let's go ahead and take a look at our agenda. So there's kind of 5 key things that we're going to talk about today. First, we're going to start with what is a spectrum analyzer, and so give you a quick overview of that. We'll talk a little bit about how a spectrum analyzer works, and as part of that, we'll talk about how that compares to an oscilloscope. And an oscilloscope is something that a lot of people are pretty familiar with, and so comparing the spectrum analyzer back to an oscilloscope can maybe clear up any confusion on how the two different or how the instruments work differently. We'll talk about key parameters and setup for a spectrum analyzer, and then we'll finish up with best practices to make better measurements. So there's some things that we can do to improve the measurements, and while most of the examples that I'll use today are from a Rohde and Schwarz spectrum analyzer, everything that we talk about really applies to any spectrum analyzer that you might use. So again, let's start with what is a spectrum analyzer. So a spectrum analyzer is also known as a swept frequency analyzer, and it measures the magnitude of an input signal versus frequency within the full frequency range of the instrument. And what I mean by that is most spectrum analyzers are going to have a top, or all spectrum analyzers will have a top end frequency that they can measure to. And, let's say that it's something like 6 gigahertz. And then they're going to typically have a low end frequency that they start at, something usually in the kilohertz range. And so the spectrum analyzer will measure within that range. You'll often see, and sometimes in this presentation, you'll see spectrum analyzer abbreviated. It can be something like SPA in all capitals, or SPA with the P being lowercase. You might see it as SPAN for spectrum analyzer. So if you see that, just know that we're talking about the spectrum analyzer in and of itself. And then in this presentation, we're going to talk about some of the typical adjustments and what those mean. And so you'll often hear people talk about either center frequency or span. You'll hear people talk about RBW, which is resolution bandwidth. VBW is video bandwidth. We'll talk about attenuator levels and reference levels. And all of those things are kind of critical adjustments within the spectrum analyzer itself. And then what do you typically use a spectrum analyzer for? Well, you're typically going to look at things like harmonics, spurious. You might look at absolute or relative frequency and amplitude. You might look at power within a specific bandwidth. There's a number of different measurements that you can make, and we'll talk through some of those. And some things you can do manually, some things it's better to do with the automatic measurements inside of the spectrum analyzer itself. Okay, so let's talk a little bit about what does a spectrum analyzer do. And when you start, so again, as I talked about before, spectrum analyzers, they're really frequency domain instruments. So they're going to show you power versus frequency. And this is by far and away the most fundamental measurement on the spectrum analyzer, this plot over here of power versus frequency. Most spectrum analyzers also automate certain measurements, so AM modulation depth, TOI, etc. And like I mentioned, these could be done manually, but there's one of the big benefits of doing them automatically inside of the spectrum analyzer is that you end up with it being typically more accurate and also just much more efficient. There's also some other measurements that you can make inside of a spectrum analyzer that'd be very difficult to do manually. So occupied bandwidth is an example of that. Adjacent channel leakage ratio, or ACLR, is another example of that. And so having a spectrum analyzer that can do those measurements for you automatically is fantastic, because in a lot of cases it'd be very difficult or impossible to do manually. Spectrum analyzers can also demodulate vector signals. So if you're looking at things like LTE, 5G, Wi-Fi, we can look into the structure and content of those signals themselves. So clearly there's a lot of things that we can do with the spectrum analyzer, but what we're going to start with and what we're going to focus on in this presentation is really just the power versus frequency. So again, we're sticking to the basics, and that's where we're going to spend the majority of the presentation today. All right, so I mentioned earlier that we'll kind of tie this back to oscilloscopes, and we'll talk a little bit about the differences as well, but most people are pretty familiar with oscilloscopes, and an oscilloscope shows you the signal in the time domain. And so what you see in the time domain is you see the waveform over time. And as we all know, waveforms are made up of a number of different multi-tone signals. And that's really where the spectrum analyzer comes into play. And so the spectrum analyzer, instead of showing you amplitude over time, like an oscilloscope would show you, it's going to show you amplitude over frequency, and it's going to show you all of those different multi-tone signals in the frequency domain that make up the actual waveform that you might be capturing with the spectrum analyzer itself. So just another kind of way of thinking about how a spectrum analyzer differs and how it works in comparison to, again, something like an oscilloscope that most people are pretty familiar with. All right, so let's take a look at a block diagram of a spectrum analyzer and talk through how a spectrum analyzer works. So basically, the spectrum comes in, it's measured by sweeping the local oscillator across the band of interest. There's a couple key things that you get out of a spectrum analyzer, a swept spectrum analyzer, and one of those is you get very low noise due to the IF gain in filtering. The sweep can be really fast over a narrow span. So as long as you aren't capturing a very, very wide area or very, very wide frequency of interest, you can have very fast sweep time. You can do things like real-time operation after the IF filter using an FFT. Spectrum analyzers get you very high SFDR, spurious-free dynamic range. So a lot of nice features of the spectrum analyzer. And as we look at the block diagram here, basically what you have is the signal comes into the spectrum analyzer, and there's an input attenuator there that's going to adjust the signal to make sure that it's in the best amplitude and the best setup to be able to be handled by the spectrum analyzer. Then we have the local oscillator, and the local oscillator is going to work with the mixer to take that RF input and convert it into an IF signal that we can filter and amplify and detect. And so this is one of the critical aspects of the spectrum analyzer. Next, we have a sweep generator, and so it's going to basically sweep across that desired RF frequency range and allow us to be able to see all of the different frequencies in there. The IF filter, it's a bandpass filter. This is where we determine the resolution bandwidth of our spectrum analyzer. And this is a pretty important feature, and we'll talk about this as we move on. But basically, a narrow RBW will improve selectivity and signal to noise ratio, but it's going to slow down the sweep speed and the trace update, and we'll talk about why that happens and kind of how to balance that as we move on. Next up is the detector, so it'll process the IF signal using different modes for display of the amplitude. There's also a video bandwidth filter or video filter. We'll talk about what that is. And then all of this is used then to actually display it onto the display of the spectrum analyzer itself. All right, so I mentioned we're going to talk a little bit about how a spectrum analyzer compares to an oscilloscope. And so with that, clearly both instruments have their place, and they both are really good at what they do. So spectrum analyzers are fantastic at looking in the frequency domain. Oscilloscopes are fantastic at looking in the time domain. There is some crossover between them, but in general, a spectrum analyzer, again, it's going to operate by sweeping a local oscillator across whatever the band of interest is. You'll see the signals in the frequency domain. You're usually going to have a smaller bandwidth capture range. And so instead of having the wide bandwidth that you get with an oscilloscope from basically DC up to the bandwidth of the scope, the capture range that you're going to have in the spectrum analyzer is going to be more narrow. You're usually going to have much better dynamic range in a spectrum analyzer, and you're usually, again, going to be more interested in signal bandwidth and level. Some of the typical applications, we talked about measuring the signal versus frequency, doing compliance testing, in like EMI testing, those types of things, interference isolation, anything that makes sense to look at from the frequency domain is where a spectrum analyzer is going to really excel. Now, in oscilloscope, we talked about it sweeps basically the signal over a time axis for the amount of time that you're interested in. You observe the signals in the time domain. You, of course, can observe them in the frequency domain as well with an FFT, but it's not going to be quite as, or it's not going to be as good as you would see in a spectrum analyzer. You do get that wide capture bandwidth, though, from DC to the bandwidth of the scope. So if you have a 1 gigahertz scope, you'll be able to go all the way up to a gigahertz of capture bandwidth. You're usually not going to have as good of dynamic range versus a spectrum analyzer. So the spectrum analyzer is going to have better dynamic range, and in particular, most of the time, less or a better spurious-free dynamic range. With an oscilloscope, you're usually interested in signal transitions and timing of signals, maybe in relation to each other. You also get multiple inputs on the oscilloscope, whereas most spectrum analyzers, it's a single input. So in oscilloscope, the typical application, you're going to measure the signal versus time. Some of the advanced applications that you might do are electrical compliance. So if you're doing compliance testing on high-speed serial signals, those types of things, transient analysis, electrical characterization, decoding of digital signals. So, you know, if you're doing decoding on an I2C bus or something along those lines. Such a quick overview of oscilloscopes versus spectrum analyzers. Now let's go ahead and take a jump into essentially what the key parameters are, and we talked a little bit about some of these, but we're going to take a deeper dive on them, and how you want to go about setting up your spectrum analyzer. And again, what we're going to talk about here while using RNS spectrum analyzers as the example, know that most of this is going to be generic and would apply to any spectrum analyzer that you might be using. Okay, so let's talk through the basic configuration parameters. And we're going to focus in on four kind of the key ones that you need to operate a spectrum analyzer. So the first one is center and span, and we'll talk through what that is. The next one is reference level. The third one is resolution bandwidth, and the fourth one is video bandwidth. And these are the settings that are most used when making essentially any type of measurement on the spectrum analyzer. And this is where most people are going to start with, and these are the critical areas that you need to understand what the trade-offs are and what the benefits are of doing different settings within them. All right, so let's start with defining the span. And the very first question that you might ask yourself when making a spectrum measurement is, what's the frequency range that I'm interested in? So in other words, what are the stop and start frequencies? And so the example that we're going to use here is we're going to have a start frequency at 840 megahertz, and we're going to have a stop frequency at 860 megahertz. And that's going to give us that window of frequency that we can look in. And we could go in and we could enter those values. Spectrum analyzers allow you to enter a start frequency and a stop frequency. But most people that use spectrum analyzers on a regular basis, they're going to enter it in a little bit different way. And they're going to enter it by using a center frequency. And in this case, our center frequency would be at 850 megahertz. And then they're going to set the span. And our span for us here is 20 megahertz. And the reason that people will go through and do this is most often we know what our center frequency is that we want to look at. So you might have a signal of interest and you know that it's at 850 megahertz. And so you'll go ahead and put that in as your center frequency. And then the other reason is it's pretty easy once you set your center frequency to zoom in and out on to use the span to zoom in and out on the signal of interest. And so if we set our center frequency at 850 megahertz, and instead, say, of 20 megahertz, we set our span to 10 megahertz, now our start frequency is 845, our stop frequency is 855, and you can see that we've essentially zoomed in on that signal. If we went to something like a span of 5 megahertz, again, we've moved in closer on the signal, and our start frequency now is at 847.5 megahertz, the stop at 840 or 852.5. And again, this is just a little bit easier method of entering the criteria to be able to look at the spectrum that you're interested in. So now we talked about that kind of in generic terms. Let me show you what it would look like on an actual spectrum analyzer. And so the way that you're going to go about this, spectrum analyzers they use will typically have a button that is labeled FREQ or frequency or something along those lines. And when you push that, you're going to be able to enter the center frequency. If you look up here in the top right-hand corner, basically we've got a spectrum here, and there's clearly some signal of interest popping up over on the right-hand side. This is where you might want to adjust your center frequency to be able to take that into account. One simple way to do this is to put a marker. And again, most spectrum analyzers are going to have a marker button on the front panel. Go ahead and turn that marker on. You can see that that signal is at 2.4 gigahertz. Now that we know that that signal is at 2.4 gigahertz, we can go in, adjust our center frequency by hitting the FREQ or the frequency button, type in 2.40, 2.401. We can get as specific as we want, and then that'll set our center frequency to match that frequency of interest that we're wanting to look at. And so that's what we've done here down at the bottom. So we put our marker on. We saw that spike was at 2.4 gigahertz, and then we went ahead and entered that as our center frequency and got a good setup there. You can see we also changed our span. So our span was at 3 gigahertz before. We've now adjusted our span down to about 1.2 gigahertz. You can, again, set the span to whatever you feel is necessary. And so that's actually kind of the next discussion. So we adjusted into that 2.4 gigahertz, and our span was at 1.2, but it's difficult to see some of the additional information on there. So again, most spectrum analyzers are going to have a button that says span on it. So you go ahead and hit the span button. And in this case, we're going to adjust our span to 40 megahertz and really zoom in on that signal. You type in 40 megahertz, and now we've been able to zoom in on the waveform. And so a couple things to keep in mind. One is the wider the span is, the slower the measurement speed is. So it's a much broader range of frequency that you have to sweep over. The narrower the span, in general, the faster the spectrum analyzer is going to be able to measure. And I say in general because there are exceptions, but for what we're talking about today, we're going to kind of take that as a rule to keep in mind. And as you can see, when we moved from this wider span at 1.2 gigahertz up here at the top down to a span of 40 megahertz, it makes it much easier to start to see some of the interesting signals and harmonics around that. Now, there's another piece that comes into play here, and we'll talk about that here in a second. But just know that as you set your center frequency and adjust your span, those are two of the key components that you're going to be looking at. All right, so after talking about center frequency and span, let's talk about reference level and defining the reference level. So reference level is essentially the top edge of the display. And so it represents the maximum expected power at the spectrum analyzer input. And so as we look at the top edge of that display, we want to be careful that we don't have the waveform off of there. So in most cases, we're going to adjust our reference level so the highest level of the signal is just slightly below that level. We want to avoid having it too high, and we want to avoid having it too low as well. So setting the reference level too high will decrease our dynamic range and the ability to see small signals and changes in amplitude. All right, so this is essentially what you want it to look like. So again, you have your reference level. It's at the top end of the screen. You want to have whatever the largest signal is on the display slightly below that. So what happens if we set our reference level too low? So in addition to causing that trace to kind of poke through the top of the screen, it can affect our measurement results. And so why can it do that? Well, behind the RF input, there's some sections of the spectrum analyzer that we talked about before that are active components. So those mixers and those amplifiers. And basically, if we have, if the input level is too high, then those devices can go into something called compression, which creates distortion, and it'll negatively affect our measurement results, and sometimes it'll severely affect them. So to prevent this from happening, a variable input attenuator is placed between the RF input and the mixer and the IF amplifiers up there. And so when we set the reference level, this value is used by the spectrum analyzer to adjust the input attenuation and or the IF amplifier gain in order to avoid overloading the instrument. And this is a really important behavior, or a really important thing to keep in mind, because it can drastically affect the measurements. And not only that, if you input too big of a signal into the front end of the amplifier, you can end up, or the front end of the spectrum analyzer, you can end up damaging it. But even outside of that, if you don't have the reference level set correctly, we can end up with results that are inaccurate. Let's talk a little bit more about the reference level. So again, if it's off the display, like you see up here in the top right-hand corner, essentially the spectrum analyzer is being overdriven. And worst case, the signals above the max input level can end up causing damage, like I mentioned. But even best case, the components, as we talked about, they're going to be in their nonlinear region, and so you're going to get less accurate or incorrect measurements. And so that's something that you want to avoid. And again, you avoid this by setting your reference level where it's just slightly below the top of the display. Okay, so let's talk about resolution bandwidth. And so resolution bandwidth is a really important setting on a spectrum analyzer. And in a lot of cases, it's actually probably the most important setting. And so most spectrum analyzers use the so-called heterodyne-based analyzers to measure the spectrum by sweeping across a span. And so the trace showing power versus frequency is drawn from left to right, usually repeatedly. So one way to understand resolution bandwidth is to think of it as like a window. And so that window moves across our span. And as it moves across our span, it measures the level as it goes. And this concept of a moving window can hopefully be helpful in kind of understanding what resolution bandwidth is and why it matters. So let's take a little bit deeper dive on this now. So usually that window, while we show it as kind of a rectangular window here, it's not really rectangular. So it actually has a Gaussian shape to it, or a similar shape of some sort. And the window also doesn't really move. So while in trying to kind of help you understand how it works, we move the window. In reality, we slide the spectrum past the window instead of the other way around. And so in part, it would be extremely difficult. Why do we do this? It would be extremely difficult to build a tunable filter that could sweep across an entire wide frequency range. In the end, the result is the same. And many RF engineers do think of the resolution bandwidth as kind of a moving window or a filter that crosses across a span. But just know that it doesn't really work that way. The way that it really works is we're going to move the waveform across this Gaussian or similar shape, whatever it ends up being. We're going to move the spectrum past that window instead of the other way around. All right, so why does the resolution bandwidth matter? Well, as the name implies, one of the things that resolution bandwidth affects is our ability to separate or resolve closely spaced signals. So for example, if we have two narrow signals, we can only separate them if our resolution bandwidth is smaller than the distance between these two signals. If we use a wide resolution bandwidth, both the tones are going to end up covered by the filter as it sweeps past, and they might appear, in this case, as a single tone now. And so that's the drawback of having too wide of a resolution bandwidth. You might end up with something that looks like down here at the bottom of the display versus what is actually happening where you see two tones, what we should actually see if we had the correct resolution bandwidth set. The other important aspect of resolution bandwidth is the effect that it has on noise. And so more specifically, resolution bandwidth affects the noise floor, and that's also often referred to as DANL, or the displayed average noise level. The noise floor rises or falls depending on the chosen resolution bandwidth. So why does that happen? Well, the noise generated within a spectrum analyzer is more or less flat over frequency. And this in turn means that the noise contained in a wider resolution bandwidth filter is greater than the noise contained in a narrower filter. So as we decrease our resolution bandwidth, in this case, we'll just use a simple CW signal with a rather large span of 2 gigahertz. As we decrease that resolution bandwidth, you can see that we go from, say, minus 73 dBm at a resolution bandwidth of 3 megahertz. As we step down to, say, 300 kilohertz, the noise floor gets better. We move from negative 73 down to about negative 84. At a resolution bandwidth of 30 kilohertz, we go to negative 93 dBm. And then as we go down to a resolution bandwidth of 3 kilohertz, we go all the way down to minus 104 dBm. And you may have noticed that decreasing the resolution bandwidth by a factor of 10 lowers the noise floor by about 10 dB. And as a practical matter, if we want to see signals close to the noise floor, we should use a narrow resolution bandwidth. All right, so you might say, well, then why don't we just always use a narrow resolution bandwidth? And that's a great question. And so remember that resolution bandwidth is essentially a filter, and narrow filters take a longer time to settle or to get stable compared to wider filters. And this means that we must sweep more slowly when using smaller resolution bandwidths in order to get accurate results. Sweeping too quickly leads to both amplitude and frequency errors. In fact, the main factor in determining the sweep time of a spectrum analyzer is the resolution bandwidth. And the good news is that most spectrum analyzers will automatically compute sweep time based on the resolution bandwidth and span that you have set. And while you can override those settings, but decreasing the automatically calculated sweep time is usually not a good idea. So this is going to be the trade-off that you end up with going to a more narrow or a smaller resolution bandwidth, is that the sweep time is going to end up taking longer. And so that's just something that you have to keep in mind. You have to find that sweet spot of the proper resolution bandwidth that gives you the noise floor that you want, the ability to resolve the signals that you care about, but also keeps the spectrum analyzer at a speed that is useful to you. Okay, so as we take a look here, I kind of want to show you what it might look like on a spectrum analyzer itself. So on the left-hand side, we have a resolution bandwidth that's pretty wide, and so you can see that we end up with a signal shape that, when we compare it to the signal on the right-hand side, where we have a more narrow resolution bandwidth, you can see that we lost some of the information there, and we lost some of the adjacent information, or we were unable to resolve the frequency of interest with the resolution bandwidth on the left-hand side compared to what we see with the more narrow one on the right-hand side. And again, as we talked about, the resolution bandwidth, it does affect the noise floor. So as we went over, a wider one lets in more noise, a narrow one lets in less noise. And so again, you kind of have that factor of 10 to reduce the noise level by 10 dB, set a 10 times more narrow resolution bandwidth. And this is a great example. Again, all the settings, kind of the display is the same. You can see over here on the left-hand side, we're a little less than negative 60 dBm. On the right-hand side, we're a little less than negative 70 dBm with a resolution bandwidth that was decreased by a factor of 10. Okay, so now let's talk about video bandwidth. And so resolution bandwidth is oftentimes called RBW. Video bandwidth is called VBW, as you would expect. And so this is kind of the last parameter that we're going to go over. To better understand video bandwidth, we need to explain what we mean by a video signal. And so the traces that we've been looking at in this presentation are essentially an envelope of the power at individual frequencies. And this envelope is called the video signal. Why is it called video? Well, in the old days, the signal was applied to the vertical deflection of a cathode ray tube in order to draw a video trace on the screen. In modern spectrum analyzers, video bandwidth is a type of filter used to average or smooth out the displayed trace. One very important thing to remember is that the video bandwidth only affects how the signal is displayed, not the way it is measured. This is unlike resolution bandwidth, so be sure not to confuse the two. So let's look at a video bandwidth example. At a video bandwidth of 200 kilohertz, we can see what looks like a fair amount of noise on our signal. When we lower the video bandwidth down to 20 kilohertz, you can see that the noise starts to look quite a bit better. It's reduced quite a bit. If we take it another step and go down to 2 kilohertz on the video bandwidth, you can see that we've really cleaned up that trace quite a bit. So lowering the video bandwidth, lowering the video bandwidth, it reduces noise on the trace, but it does not drop the noise floor like resolution bandwidth does. And it also does not improve our ability to resolve or separate closely based signals. So you can kind of think of this as it's basically just cleaning up the display, and again, kind of almost like an averaging on the waveform itself. So giving you another opportunity to see it on the display of a spectrum analyzer. The top one, we have the video bandwidth set to 1 megahertz. When we adjust it down to 300 hertz, you can see that it's really cleaned up the display quite a bit. Video filtering is part of the data signal, the digital data processing. And so while it will reduce the peak-to-peak variability of a noisy signal and give you better trace readability, keep in mind it can also slow down the spectrum analyzer a little bit as well. And the last thing to keep in mind is that, again, that signal amplitude is unchanged by the narrower video bandwidth. And so, again, this is really, I kind of think of it as cleaning up the display versus resolution bandwidth is actually changing the way that we are capturing the information itself. Okay, so let's talk through some best practices to better measurements. And in general, when you look at a spectrum analyzer, you're usually going to have something that says preset or default setup, something along those lines that allows you to go back to a known good state. And I highly encourage you to always start with that. Make sure that you hit the preset button to start with, because then you'll know that you're in that kind of original state. The first three settings that you're going to want to look at are center frequency, the span that you want to look at, so the frequency span, and the reference level. Again, you're going to set reference level equal to the highest signal, and you're going to want it to be slightly below the top of the display. You can use those markers like we talked through earlier to be able to identify the frequency of interest that you want to look at, and then use that to set your center frequency and then adjust your span. And again, a narrower frequency span will improve the speed of measurements. And for RBW, a wider RBW will increase the speed, but keep in mind that you want to have a proper RBW that gives you both the noise floor that you need to resolve the signals that you're looking at, but also the resolution that you need to be able to resolve signals that might be close to each other. So again, as we choose that RBW, the optimal bandwidth is almost entirely a function of the signal being used. And it's often going to be something that you kind of have to experiment with. So remember that there's a trade-off between speed and, again, that selectivity and the noise. If we decrease resolution bandwidth, that will increase our selectivity. So again, the ability to kind of resolve nearby signals. Narrowing the resolution bandwidth will also drop that noise floor like we talked through, making it easier to see weak signals that might be hidden otherwise. But as we've seen, again, that sweep time will increase, and in some cases it can rapidly increase. And so just something to keep in mind there. So in other words, small resolution bandwidths lead to very long, perhaps unacceptably long sweep times. And so just keep that in mind. One final note on spectrum analyzers, you can't choose any arbitrary, on most spectrum analyzers, you can't choose any arbitrary value for the resolution bandwidth. And so you kind of have to select it in steps. And so those steps might be 1 through 10, or in a 1, 3, 10 sequence, where you might end up with something like a resolution bandwidth that's available at, say, 1 kilohertz or 3 kilohertz or 10 kilohertz or 30 kilohertz, that type of steps. I highly recommend leaving the resolution bandwidth in auto whenever possible. Again, you'll want to decrease it to resolve those closely spaced signals. You'll want to decrease it to accurately measure the signal shape, and you'll want to decrease it to reduce the noise floor. Let's talk a little bit about choosing VBW, so the video bandwidth. So again, video bandwidth, it only changes what the trace looks like. So to a certain extent, the correct video bandwidth setting depends on the application. That said, most spectrum analyzers, or modern spectrum analyzers, will automatically configure the VBW based on other parameters, so things like the resolution bandwidth. And so it's going to try to find the best setting for the VBW to make sure that you are getting, again, a good sweep speed and something that allows you to see the signal that you care about. In many cases, a smaller or more narrow video bandwidth might seem desirable since it reduces noise on the trace. But as we talked about before, video bandwidth does have an effect on that sweep time. So just keep in mind that the more narrow the VBW, the longer the sweep time is going to take. Okay, so best practices for VBW. Again, I would leave in auto unless otherwise required. Use it to smooth out that noise, but don't lower it too much, because you'll end up with something that will slow down the spectrum analyzer potentially to a speed that makes it unusable for you to for the application that you're looking at. Okay, with that, thank you very much for your time today. Greatly appreciate it. And now we'll go ahead and open it up to questions.
Thank you, Rich. So if anybody has questions, please just go ahead and drop them in the Q&A box, or you can also raise your hand and we can unmute you to ask your question. I did get a couple comments throughout the presentation. Sometimes the images were coming through a little bit blurry on the presentation slides. So when we send out the recording of the presentation, we can include those slides as well. So Rich, I have a question here on my end. This person's just asking, why, when you have a wider frequency span, does the measurement speed slow down?
Yeah, great question. So, you can imagine, as you have that larger span, looking at a bigger capture window, it just takes more time to process. And so that's going to be one of the main pieces that fall into why that slows down.
Great, thank you, Rich. We have another one in the Q&A box. What's the best way to determine whether I'm looking at a narrow or wideband?
So I think I understand the question. Basically it's going to all depend on how wide the frequency range is that you're looking at. And so if it's a more narrow band signal, clearly you're going to be looking at a narrower capture bandwidth. And if it's a wider band signal, a larger signal, then you're going to be looking at more of a wide band capture.
Okay, great. We've got a few more questions in the chat. I think they came just to me, so you might not be able to see these ones, Rich. From Omar, he's asking, in microwave communications, is it always necessary to disconnect the waveguide from the antenna port to connect to the spectrum analyzer?
I actually am not an expert on that area, so I think that's probably a great one for us just to follow up with. I think you said it was Omar that had asked that for us to follow up with Omar on that, and we'll make sure that you get the right answer there.
Okay, yeah, thank you, Rich. Good question, Omar, and we'll follow up with you after today's webinar. We have another question here from Richard. He's asking if you can briefly describe FFT.
Yeah, so FFT it stands for fast Fourier transform, and it's a mathematical way of breaking down the frequencies within a signal. So if you look at a really any signal out there, it's made up of a number of different tones, and an FFT allows us to break those tones down into their individual segments. And FFT is pretty commonly used to allow you to see the frequency uh, portion of a signal. So, if you're looking at something like a square wave, it's going to be made up of a number of tones, and you can see each of those harmonics, and an FFT is used to do that.
Okay, great. There's another one there in the Q&A box from Wes asking, what would LMR be considered as, whether it's narrow or wideband frequency, 150 megahertz VHF
VHF, yeah.
versus 700 to 800 megahertz UHF?
Yeah, and again, so Wes, that's a great question, and unfortunately, I'm not an expert in that area. So I think this is another one that we may want to take offline and just follow up with Wes directly on, uh, and we can help there.
Okay, great. Yeah, thank you, Rich. Okay, just made notes to follow up with both of you. One other question here. What is the benefit of using a center frequency when defining the span?
Yeah, so you have two different ways of being able to define the span. You can use a start and stop frequency, or you can use a center frequency. I prefer the center frequency when I know the frequency content that I'm looking at. So, for example, if I know I want to look at a 1 gigahertz signal with 20 megahertz of span around it, I will typically set my center frequency at 1 gigahertz and then set my span at 20 megahertz. The other way you could do that is you could just set the start and stop frequency at 990 megahertz and 1.01 gigahertz. But I think it's easier to use a center frequency in that situation. But it's really user preference, I would say.
Okay, yeah, great explanation. We'll just give another minute for any questions, any last questions. If not, we'll wrap up. And if anybody thinks of any questions after today's presentation or once we've sent the recording out, please feel free to reply to my email or reach us at marketing@testforce, and we can pass your question along to Rich or connect you with the right person to get your answer. Okay. Oh, we've got one more question actually that just came through. Does changing the RBW and reference floor changing, does that affect the actual level of the signal you are looking at?
Um, it doesn't affect the level of the signal. So the signal is what it is. The benefit of going to a more narrow RBW is you'll lower the noise floor of the spectrum analyzer, which will allow you to see, have more dynamic range and allow you to be able to see tones that may be hidden in the noise of the spectrum analyzer more easily. So it doesn't really affect the signal that you're looking at. It just gives you a better ability to see it. But of course, keep in mind there's always trade-offs, right? So as you lower the RBW, again, it becomes a much more intensive uh, piece of work for the spectrum analyzer, and it can slow the spectrum analyzer down from that perspective. But you definitely gain additional insight and dynamic range.
Okay, thank you, Rich. So if there's no other questions, we'll wrap up this morning. I just want to say thank you to our presenter, Rich Markley, for being on with us this morning. And thank you to everybody for signing on and for your great questions. So we'll be sending out the recording of today's presentation later this week. And you can rewatch that at any time. So thank you all, and I hope you have a great day.